Assalamualaikum warahmatullahi wabarakatuh. I hope everyone is doing well. So for this week, I will try to finish the last topic in chapter 4, which is chapter 4D. So in this topic, it will include topic adder, decoder, encoder and multiplexer in digital system. So after finish cover this chapter, students should be able to use MSI devices. So this means that a student needs to know each and every function of MSI devices and how they work within the digital system. So what is MSI devices? So MSI device is a medium scale integration device that have a complexity of approximately 10 to 200 gates or transistor in a single IC package. Okay, so this means during the circuit fabrication, the process has embedded hundreds of transistors in one integrated circuit or microchip. So at the early stage of integrated circuit design, the first integrated circuit contains only a few transistors, and we call it as a small scale integration or SSI. So they use circuits containing transistors numbering in the tens. Okay, it means a small number of transistors. Okay, so they were very crucial in development of early computers. So SSI was followed by introduction of the devices which contain hundreds of transistors on each chip. Okay, so we call this as a medium scale integration. So this is what we're going to focus in this chapter. Okay, so MSI were attractive economically because they cost little more system to be produced using smaller circuit board, less assembly work, and a number of other advantages. Okay, so next development was a large-scale integration. We call it as a LSI. Okay, means there are a few stages. Okay, the production of integrated circuit is starting with SSI and then MSI, and then after MSI we call it as a large scale integration LSI. So the development of LSI was driven by economic factors, and each chip comprised tens of thousands of transistors. So it depends on the number of the transistors. So usually the MSI devices perform specific elementary digital function for logic and arithmetic logic circuit, which is listed here. Okay, so these are among function of MSI. Yeah, but for this chapter, for chapter 4D, we only focus on decoder, decoder, encoder, multiplexer, and adders. Okay. So the first MSI device we will cover is adders. So what is adders? Okay. So an adder is a digital circuit that performs addition of numbers. Okay. In many computers and other kinds of processor, address are used in the arithmetic logic unit, or we call it as a ALU. Okay. So they are also used in other parts of the processor, where they are used to calculate addresses, table index, increment and decrement operations, and similar other operation. Okay. So since adders are widely used in computers or processor, so we need to know how they operate. Okay. So although adders can be constructed from for many number representation, such as a binary coded decimal, the most common adders operate on binary numbers. So this list shows the basic rule for binary addition. So you still remember in chapter 4a, so we already learned about the addition of a binary number. So this is the basic rules for binary addition. Okay. So for this one, 1 plus 1, so actually in decimal is equal to 2. But in binary number, 2 is equal to 1, 0. 1, 0 means if you convert to decimal, so 0 times 2 power of 0 plus 1 times 2 power of 1, so equal to 2. So 2 is the decimal number. 1, 0 is a binary number. Okay. So this operation can be performed by a logic circuit. We call it a half adder. So this operation can be performed by a logic circuit called a half adder. So the half adder adds two single binary digit A and B. So let's say we have these two variables A and B. So half adder will add these two single binary digit. Okay. So it has for half adder, it has two outputs. Okay. Half adder we have two output. We have sum and carry. So this is output for half adder. So this is the schematic diagram. Schematic diagram or symbol for the half adder circuit. Okay. So the carry signal represent. So the carry signal, okay, represents an overflow into the next digit of a multi-digit addition. So the simplest half adder design. So this is the half adder circuit. So this is the half adder circuit. For the half adder, incorporate an XOR gate. So this is XOR for the sum operation. So this represent sum. And an AND gate. So this is AND gate for C, for carry. yeah, for carry operation. Okay, so the Boolean logic for the sum will be A bar B plus AB bar. So how we get this equation? Yeah. So this is equation for sum, for the sum. So we can get this Boolean equation from this truth table. Okay. So you refer output 1 for the sum operation. So for output 1, the minterm is A bar dot B, yeah, and A dot B bar. So this is the Boolean function for sum operation. Okay. Whereas for the carry, the Boolean function is AB. So we refer to the truth table. Okay. So only this condition give output 1 for carry. So the minterm for carry is A dot B. Okay. So you refer back your lecture note in chapter 4b. Yeah. So refer to what is minterm. Okay. And then from here we can get the Boolean function for each operation, yeah, for sum and carry. So the half adder adds 2 input bits, yeah, add 2 input bit which is A and B, and generates a carry and sum, which are the 2 outputs of a half adder. Okay. And from this Boolean function, so from this Boolean function, we can design the half adder circuit. So this is how the circuits looks like. Yeah. Okay. So because A B bar plus A bar B is equal to A XOR B. So this is A XOR B. Okay. And AB means A multiplied by B. So we need to have AND gate to do this operation. Okay. Okay, now we have full adder. Okay. So a full adder adds binary number and account for values carried in as well as out. Okay. So a 1-bit full adder adds 3 1-bit numbers. Okay, often written as A, B, and C in. So for full adder, so we have 3 input for full adder. We have A, B, and C in. Okay, carry in. A and B are the operands, and C in is a bit carried in from the previous less significant stage. Okay. So the full adder is usually a component in a cascade of adders which add 8, 16, 32 or other bit binaries number. Yeah. The circuit produces a 2-bit output. So the output from the full adder, we will have sum and output carry. So output carry and sum typically represented by the signal Cout and S. Okay, so this represent the output from the full adder. So we have Cout and S or sum. Okay. So a full adder can be implemented in many different ways, such as with a custom transistor level circuit or composed of other gates. So one example implementation is with S equal to A XOR B XOR Cin. Okay, that's for output sum. Yeah. So this is the output for sum operation. So A XOR B XOR Cin. Okay, and for Cout is equal to A B plus Cin A XOR B. Yeah. So this is the operation or Boolean function for Cout for the full adder. Okay. So a full adder can also be constructed from two half adders by connecting A and B to the input of one half adder and then taking its sum output as one of the inputs to the second half adder and Cin as its other input. So we can design. Yeah. So this is considered as one. So for this one, yeah. So this consider the operation for sum. Okay. So this is for sum. Okay. And we also can design a full adder logic by a combination of two half adder. So if you realize, so this actually one half adder. Yeah. So this is one half adder. Yeah. And this is another one half adder. Okay. So we have two half adder to generate one full adder. To design one full adder. Okay. So the output sum. So this is output sum from the first half adder can be the input for the another half adder. Yeah? And then we need to have one OR gate, yeah, to complete the operation for the Cout of full adder. Okay. So the sum output from the second half adder is the final sum output as of the full adder, and the output from the OR gate, yeah, the output from the OR gate is the final carry output for the full adder. So this Boolean function for sum, yeah. So you can get this Boolean function if you consider this output 1 for sum. Okay. So you can simplify the sum. Yeah. So this is we call sum. Yeah. So actually sum, the Boolean function for sum is A bar, B bar, C in plus A bar, B, C in bar plus A, B bar, C in bar and plus A, B, C in. So if you simplify this Boolean function, so you can get this equation. So you can simplify it using Boolean algebra and you will get this kind of Boolean function. Okay, meanwhile for C out, so the Boolean function for C out, so C out is A bar, B, C in plus A, B bar, C in, A, B bar, C in plus A, B, C in bar plus A, B, C in. So this is the Boolean function for C out. So if you simplify this Boolean function, so you get this Boolean function, for C out. Okay. So for the full adder circuit, so this is how the logic circuit looks like. So if you combine two half adder circuit, okay, and this full adder logic circuit, can be represented by using a symbol or schematic block diagram. So this is how the schematic looks like. So inside this block diagram, so all this logic circuit is actually inside this block diagram. Okay, so the logic circuit of full adder can be replaced by a schematic block diagram of two half adder. So this is considered the first half adder. So this is the first half adder and this is the second half adder. And this schematic diagram also can be represented by a single block diagram of full adder. Okay, so this all this schematic diagram can be represented by a single block diagram of full adder. So now we consider the second MSI device, which is a decoder. So what is decoder? So the name decoder means to translate or decode coded information from one format into another. Okay, so a decoder is a multiple input, multiple output logic circuit which convert coded inputs into coded output, where the input and output codes are different. So the input code generally has fewer bits than the output code. Okay, means the input bilangannya sedikit, okay, berbanding dengan outputnya lebih banyak, okay, for decoder. Okay, So each input code words produce a different output code words. For example, normally we have a binary decoder. So a binary decoder will transform an binary input signal into an equivalent coded equivalent code using 2n output. Okay, 2 power of n outputs. Okay, so means if you have 3 inputs, yeah, so 3 input bits, so the output is 2 power of 3, so means you have 8 output for the decoder. So normally the input code for decoder is BCD, binary. We call it as a binary coded decimal, yeah, where each decimal digit is represented by a fixed number of binary bits. So apa maksud dia? So what is BCD? Yeah. So we know that binary decimal, yeah, decimal is a normal number. For example, 0 until 7, yeah, 0 until 7, 0, 1, 2, 3, 4, 5, 6, 7, yeah, 7. So this is decimal number. So normally decimal number, if represent in binary, yeah, so 0 means 0, 0, yeah, 0, 0, 0. Okay, 1 is 0, 0, 1. 2, 0, 1, 0. 3, 0, 1, 1. 4, 1, 0, 0. 5, 1, 0, 1. Yeah? 6, 1, 1, 0. 7, 1, 1, 1. So this is what we call as a BCD, binary coded decimal. Yeah? So because this represent this binary number is equal to this binary to this decimal number. Okay. Okay. So now let's consider the 2 times 4 decoder that has active high inputs and output. Okay. So this is the 2 multiple 4 decoder, yeah, with high input and output. So this simple example, yeah, of a 2 to 4 line binary decoder consists of an array of 4 AND gate. Yeah. So this is the block diagram, yeah, or symbol or schematic diagram for 2 to 4 decoder. So inside this decoder, so this is the logic circuit looks like. So this is logic circuit for 2 to 4 decoder. Yeah. So this is how the logic circuit looks like. Yeah. So we have 4 AND gates. Yeah. So each output represent one of the minterm of the 2 input variable. So we have 2 input variable, which is A and B. So meaning that based on the output in the truth table, yeah, for the 2 to 4 decoder, so this is the truth table for the 2 times 2 times 4 decoder. Yeah. So in the truth table, where we have output DO, so DO, so if you refer to output DO, so this is output DO. So only one condition give output 1. So the Boolean function for output DO, so this is the Boolean function for output DO, is equal to A bar B bar. Okay, and for output D1, so this is output D1, so only this condition give output 1. So from here, the minterm for output D1 is A bar, A bar B, A bar times B, okay. And for output D2, so the Boolean function for output D2 is A B bar, okay. So A B bar. And for output D3, the minterm is A B, okay. So based on this Boolean function, so you can design this circuit, So this logic circuit is actually based on this Boolean function, okay. So the binary inputs A and B determine which output line from D0 to D3 is high at logic level 1, while the remaining output are held low at logic 0. So only one output can be active or high at any one time. So therefore, whichever output line is high, identify the binary code present at the input. So in other words, it decodes the binary input. Okay, so means at one condition of input, so only one output will give output 1. So if D0 give output 1, means the input from A and B is 0, 0. Okay, so it decodes the binary bits, okay. So let's say here we have a combinational logic function that is expressed as a sum of minterm. Okay, so sum of minterm means sum of product, sum of product. So therefore can be implemented by summing decoder output. So for example, so if function of variable A and B, is equal to sum, so this refer to minterm, minterm, okay. Minterm 0, 2 and 3. So then function of A and B is equal to D0, D2 and D3. Okay, so F can be implemented by the circuit shown in figure 2. So if you still remember, so you need to check the equation for this function. So if you can see here, so the highest number is 3, okay. So 3 is in decimal, okay. So if you convert 3 into a binary number, so 3 equal to 1, 1, so means the number of variable involved for this Boolean function is only two variable, which is A and B. So you can draw the truth table, so you have input A and B and F is your output, okay. So the highest, so we're gonna have input 0, 1, 2, and 3. So if you convert this decimal number into a binary number, yeah, so 0 is represented by 0 and 0. Okay, so 1 is 0, 1. Okay, 2, 1, 0. So 3 is 1, 1. Okay, so this is your truth table looks like. Okay, so the number of input, possible input, is depend on the number in the Boolean function. Yeah, so if in the Boolean function, let's say the number in the Boolean function maybe up to 7, maybe 0, 1, 7. So means the variable for your truth table, yeah, for your Boolean function, maybe involve up to 3 variable, because 7 is equal to 1, 1, 1, 1, 1. Okay, so means you need to have A, B, C. Okay, so means your truth table is from 0 to 7. So you need to have 8 input. Okay, so if the Boolean function, yeah, has a decimal number maybe up to 2 digit, yeah, for example 0, 2, 10, let's say 10. Okay, so means the variable involved, in your truth table, so it's up to 4 variable, A, B, C, and D. Because if you convert 10 into a binary number, yeah, 10 is equal to 1, 0, 1, 0. Yeah, okay, so it involves 4 binary numbers. So you need to have input, possible input, yeah, from 0 until 15, yeah, 0 until 15, because we have 4 variable. Okay, because 2 power of 4 is equal to 16. Yeah, okay, so back to this example, yeah. So for this one, we only have 2 input variable, which is A and B. Okay, so the Boolean function for this one is sum of 0, 2, and 3. So this equal to function of A, B equal to D0 plus D2 plus D3. Okay, so this is the output from the decoder. So 2 times 4 decoder, 2 to 4 decoder, means we have 2 input. Yeah, so this refer to 2 input, and 4 refer to 4 output. Okay, so because if you follow this formula, 2 power of n, yeah, so now we have 2 input, yeah, n is the input number, so we have A and B, so 2 power of 2 is equal to 4. So you have 2 inputs and 4 output. Okay, so this is the 2 to 4 decoder looks like for this Boolean function. Yeah, okay, for this Boolean function. So you need to have OR gates, yeah, to complete this sum operation. Okay. So question from this diagram. So obtain Boolean expression for the function f and simplify it. Okay, what is the Boolean function for this decoder circuit? Okay, so from here, so f equal to 1, yeah, only for input 0, yeah, input 2, yeah. What I mean is decimal equal to 2, yeah, 1 0, and input 3, yeah. So for input 1, the value is 0. Okay, so from this truth table, we can extract the Boolean expression or Boolean function. Okay, so f equal to, so you need to consider only output 1. Yeah, so f equal to a bar dot b bar plus a b bar, yeah, plus a bar a b. Okay, so this actually, okay, also equal with sum of 0, 2 and 3, and also equal to d0 plus d2 plus d3. Yeah, so how to simplify this Boolean function? Yeah, to simplify it, okay, so you can use Boolean algebra. Okay, so from this Boolean function, okay, you try to find which variable is similar, yeah, for each minterm. Okay, for example, for minterm 1, so for this minterm, yeah, and this minterm, so b times a bar times plus a, okay, plus a b. So this one, yeah, so if you refer to Boolean algebra, is equal to 1, yeah, so you can simplify it into b bar plus a b. Okay, so this is how we simplify the Boolean expression or Boolean function. Or we can have another Boolean equation, yeah. So if you consider the other literal or variable, yeah, you can simplify like this. Okay, so from here you can see that a bar dot b bar plus, so here we have a as a middle variable, yeah, and we can simplify like this, b bar plus b, yeah. So b bar plus b is equal to 1, yeah, is equal to 1. So we can have a bar dot b bar plus a. Okay, so there's two ways how we can simplify this Boolean expression, Boolean function. So decoder also has a active low decoder. So an active low decoder is the same thing like active high decoder. but with an inverted en input and inverted output. Okay, so the operation, the truth table for low decoder is opposite with the truth table for high for active high decoder. So a combination, let's say here we have another example, a combinational logic function that is expressed as a product of max term. So because active low decoder is opposite, the operation is opposite to the operation of active high decoder. So for active high, we consider SOP, sum of product or min term, but for active low, we consider max term. Max term means POS, product of sum. So therefore, it can be implemented by ending decoder output. So for for active high decoder, we use OR gate, but for active low decoder, we use AND gate, because we want to do the product of sum. Okay. So for example, if we have function of variable a and b is equal to, so this refer to max term. So this is max term. Max term 0, 1 and 3. So then function of a and b is equal to d0 times d1 times d3. So f can be implemented by the circuit shown in figure 4. So this is how we perform this operation. So you need to add AND gate, AND gate to do the product of sum operation. So means d0 times d1 times d3. Okay. And then if you refer to this, you also can draw the truth table for this decoder. So we have A and B as an input and F as an output. So since the highest number is 3, so means we have 4 possible input: 0, 1, 2, 3. Okay. So 0 means 0, 0. 1 is 0, 1. 2, 1, 0. 3, 1, 1. Okay. Since 0, 1, 3. Okay. So because this is max term, so F is 0. 1 is 0. 2 is 1 and 3 is 0. So the Boolean function for this equation is A plus B plus C and with A bar, sorry, there's no C. Okay, A bar plus B and with A bar plus B bar. Okay, so remember the max term is opposite with the min term. Okay, so F equal to A plus B times with A bar plus B sorry, A plus B bar. Okay, and then end with A bar, B bar. Okay, so this is how uh, the Boolean function for this example. So this is one of the example of commercial decoder with active low. 74 times 139 dual 224 decoder. This is the commercial IC device for 224 decoder. Okay, so as you can see here, there are two set of decoder in one IC package. So this is consider one set. So this is one set, and this is another one set of 224 decoder. And this decoder also has another input function which is called as enable. So we have another input function, we call it as a, so this is another input function instead of A and B, so we call it as a enable. Okay, so what is the function of enable? So this additional input pin label enable can control the output from the device. So this extra input allow the decoder output to be turned on or turned off as required. So this is like the main switch. Okay, the main switch on or off for your decoder. Okay, so we stop here. Okay, for now, and then we will continue our lecture for chapter 4D in the next class. Okay, thank you for your attention.